All right, we're back with a continuation from chapter 9. So I should probably notate up here. This is from 9.3, dealing with area of rhombus. So we already said that we know our area formula is 1/2 the first diagonal times the second diagonal. We already talked about the fact that a rhombus has all congruent sides. So a rhombus is like a square that gets like pivoted, or like if you grab the two corners and just yank them, the sides stay the same length, but they're no longer perpendicular at the corner. But the cool relationship is they're perpendicular at the intersection of the intersection of the diagonals, and that those bisect each other. So if I can get this to cooperate. So those are perpendicular. And Alex pointed out that it looks like I could use this second triangle rule right here because I have a 60-degree angle. So what length, if I look at my rhombus and I break it up into triangles, let's go ahead and code one of these. Look at just this triangle. What side do I know?
The hypotenuse.
The hypotenuse, right? So the side that I have right now is the 2x version, or like the 2x representative.
Which means x is 3.
Which means x is 3.
So the bottom is 3, which means the whole.
So
diagonal
this
there is 6.
has to be 3. And that means this has to be 3, since we know that the diagonals bisect each other. So then if I want to know what this edge is, the other leg of my triangle, or this edge, which they're going to be equal, how do I solve for that?
Use Pythagorean theorem.
We could, but actually it's already been done for us. Instead of having to work the whole Pythagorean theorem process, if my short leg is x, and my longer leg is radical 3 times x, that longer leg is going to be radical 3. Now what was x? 3. So it's radical 3 times 3, and this is radical 3 times 3. So I'm going to move over to the next slide and copy everything that we know that's important. So we said that this is 3 and this is 3, and this is radical 3 times 3. Now wait, if I want to like unsimplify radical 3 times 3, if I want to put it all together as one radical, how could I do this?
Radical 9, maybe?
You're close.
Wouldn't it just be 3 because radical 9 is 3?
So, I just wanted to review this really quick because some people are having issues. If I want to unsquare root it, this 3 becomes 9, but what you end up with is radical 3 times radical 9, and that would give me radical 27,
Where did the radical 9
because 3
times 3
is the square root of 9. 3 is the square root of 9, so I can replace 3 with the square root of 9. I could replace the square root of 9 with 3. They're interchangeable because they are the same thing. They look different, but they are the same. Does that make sense why they're the same? Because they represent the same value. So, I could do that, but it's not necessary. What I think is more necessary is just rewrite this with your integer value out front. 3 times radical 3. And that means that this is also 3 times radical 3. So if I want to look at diagonal 1 and diagonal 2, let's call diagonal 1 my blue one. What's the whole length of diagonal 1? This part's 3, and that part's 3. 6. Diagonal 2 is where it gets more difficult. If I have 3 radical 3's and another 3 radical 3's, what's 3 radical 3 plus 3 radical 3? Well, instead of having something plus itself, We could also just say I have 3 radical 3s. Right? Because I have 3 radical 3 here, I have 3 radical 3 here, so that length will be double that. What's that come out to be? Some of us have some issues with this still. Well, if I think about 2 times 3, that gives me 6. Is it 6 radical 6? 6 radical 3? Does it stay the same? Does this 2 multiplier affect my radical? I forget if we went over this in class or I went over this with an individual person. What if instead of saying 3 radical 3, I call this 3x, and I call this 3x? Because now x is just radical 3. So if I had 2 times 3x, what would I end up with? 6x. Does this multiplication of 2 really affect my x? No, it affects the coefficient. So this is still just radical 3. That's one place where people are falling into a trap, is when they try to find the length of the combined diagonal. They're like combining their radicals. No, this is like an unknown. We can represent it with a variable. Although I know what it is, I could set it up as 3x to make my life easier for a moment, and then replace my x back with radical 3. So now that I know diagonal 1 to diagonal 2, I can solve this. Let's say my area will be half of 6 times 6 radical 3. And from there, we can solve it out and should get what was on the answer key. That makes sense? Because then half of 6 is 3. 3 times 6 should get 18 radical 3. Is the answer key is the simplest form that they have 18 radical 3. And then it'd be feet squared. Should be. So then the other kind is number 30, right? Because 31 is kind of set up the same as 29. It's got a 30 degree. So we know that this angle in here is a 60 degree. And I can use the same 30, 60, 90 special right triangle relationship to solve that. I have my short leg. So here, this will be your x value. If we relate it down to the 30, 60, 90, that's going to be my x value because it's opposite my 30. And I can work my solution from there. So let's forget about 30. So 29, or sorry, let's forget about 31, 30. I see one angle that's 45. What do I know about these diagonals? Where they bisect? Where they intersect? It is...
They make right angles.
They make right angles. So that's 90 degrees. And if that's 90 degrees, then I know that this angle must be 45. So I have a 45-45 special right triangle. What that tells me is both of my legs have to be the same length. So if this is 4, then this is 4, and this is 4, and this is 4. Well, now I know both of my diagonals. I could set up that my edge lengths will be radical 2 times 4, but it doesn't matter. I don't need my edge lengths. All I need is my diagonals. So when I come over to 30, I forget that my laptop is not as updated as my computer. I just set up this is 4, this is 4, and this is 4. And honestly, somebody asked me, wait, where does this 4 go? Does it go with this leg or does it go with this leg? And I said yes. Because it doesn't matter. The reason they set this up like this is when you ask the question, what part of it does it go with? If they're not specific, there might be a reason. It can go with either. It can go with both. So I know my diagonals are both 8. Half of 8 times 8 will be your area. These are come out to be 32 meters squared. Any other questions from that 9-3 homework?
Just because it's the diamond, I'm sorry.
Just because what?
Because it's the diamond.
Don't call it a diamond, call it a rhombus.
Rhombus.
Because diamonds don't necessarily have the same properties as rhombuses. And we don't even use diamond as a technical shape, we use kite.
Okay.
So be careful.
Sorry, I meant to say rhombus. How could you tell it was a rhombus?
Oh, they told us.
Oh.
In the problem, it said for the rhombuses, find the area of each rhombus. Yeah, so we were informed that it was a
Why
rhombus.
weren't
What do you mean? Why weren't the diagonals of which other ones?
29, why weren't the diagonals both equal?
The diagonals aren't always equal. They bisect each other. So the fact that this is a 45, 45, 9. So if I blow up one corner of this, let's say
I blow up this corner, right? What I get and let's say that this 4 went here. So, to start, this is all that I know. But what I know is that this edge is determined by the size of that angle. And this edge is determined by the size of this angle. Well, that makes me think, well, what's that angle? Since I know this is 90 and this is 45, I know that this angle has to be 45 degrees. And since I know that these two angles are the same size, I know the legs opposite them will also be the same size. Does not work the same with a 30, 60, 90. The only reason this works like that is the angles are identical. Make sense now? Okay.
other questions from 9-3, trapezoids or rhombuses? Yeah, Hannah. 22. Ah, so this is similar to question 6, right? Yeah, so I'll solve this one. Did you watch the video that I had posted?
Oh, yeah.
Did you watch the whole thing?
Yeah.
Good, because the first part of it, I solve it the complicated method, and then I do the simpler method. This is harder than 6, right? You probably figured that out, and that's why you're asking about it. So what have you tried so far?
I don't know where to start, so.
Can you think about what we just used and make any connection with this shape and the shapes that we were just dealing with? It's a 30, 60, 90 because they've already dropped the dotted line that makes my triangle. So I could use trig, always. Trig will always work, and I actually used trig while I was putting in new trim at my house this past week. So I had, just to show you guys the practical application of why this matters, I had my floor coming along like this, and I needed to put a trim piece right here, but I had a set of stairs coming down like this. So I was going to have this really awkward cut right here that I wanted to make look really good because the trim piece comes along flat, and then it's supposed to follow the angle of the stairs. So what I did was I measured what is this height, what is this length, and I used trig to set the angle of my saw blade. It came out perfect. Not trying to toot my own horn, trying to tell you that math is really applicable beyond what you think about in the classroom. Like, you'll get to a point in your life where you're like, oh, this was useful. I'm actually glad that my math teachers taught me that. So trig will always work, but trig is the harder route to get there. And in this question, trig won't work. Well, it'll work because we know two things. For trig to work, you always need to know two things. So here, we know a length and an angle. I could use the trig, but that's not the easiest method. The easiest method is identifying that if this is a right angle, this is a right angle. You're good with that, right? And if that's a right angle and that's 30, this has to be 60. So from there, I can think back to my 30, 60, 90 special right triangle rules. In a 30, 60, 90, short side is opposite to 30. Well, if I come back to that, let me drag this up here actually. If I come back to this, well, okay, short side, I don't know what it is. But what we do know is that this will be my shortest side, or shortest leg. So, what I do know is the hypotenuse, right? Because if I look at this triangle, this 8 would be my hypotenuse. So this 8, I can represent, and actually I can make that question mark x if we're going to relate it to my 30, 60, 90 relationship. That hypotenuse is what value in the 30, 60, 90? Well, it's 2 times the shortest leg.
So that 8m is really 2 times x, which can then tell me that this height has to be if it's opposite the 30, we know it's the shortest side. The longest side, the hypotenuse, is double your short side. So if my hypotenuse is 8, and that's double my short side has to be 4. Now, that helps me with the height of the image. But is this a square?
Well, it's not a right angle over there. So,
Actually, that's a really good point. It kind of looks like a square, but we're not 100% certain that that's a right angle. Now it should be because it's a trapezoid, right? So a trapezoid should have a set of parallel lines. So actually, it telling me that it's a trapezoid, we can infer that these are parallel, and then we could infer that that's a 90, even though I didn't draw that as a very good 90. And we could actually work through the proof to see that that's a 90. But even if that was a 90, even if it was notated as a 90, does that make that a square? No, because I don't know anything about the side lengths. So the next thing I need to figure out is what is this length right here so that I can determine what this length right here is and know what my top base. Because in order to use my trapezoid formula, I need to use the top base. And you may have noticed actually Jeff Webb commented back on one of my videos on YouTube and said, well, the other route is you can just break this up into a triangle and a square. I said, well, yeah, of course we can, or a triangle and a rectangle. Sometimes it's a square, sometimes it's a rectangle. And of course we can, but make sure you understand how to deal with any trapezoid, not just one that breaks up easy. So this, I'll show you both routes. So to solve this side's opposite my 60. Right? So if I go back to my image of my 30, 60, 90, get out of here. My 30, 60, 90, well, across from my 60 is radical 3 times x. So I can use that knowledge to say across from my 60, this is going to be radical 3 times the x, and quite frankly, I wish they would put the x in front automatically. I don't like integer values coming after the square root symbol. We'd rather put them before. So we know what x is. X is 4, so this is 4 radical 3, which will for sure makes this not a square, because if this is some weird radical value, then this is probably going to become some weird radical value. So I know that's 4 radical 3. Sweet. I'm going to drag that right here just to stay out of the way. Now shoot, 4 radical 3 away from 15. It's quite messy, right? Anyone have an idea of what we could do? Can I turn 15 into a radical value? Can I turn 15 into a radical value? And then my following question will be, can I turn this into just a radical value? So, to take something from an integer form and turn it into its radical form, we need to see what two values are completely equal. Well, to look at the square root of something equals 15, this is going to have to be 15 squared. So all I need to know is what's 15 squared? What is it?
So, do you know what 15 squared is?
125.
Not 125.
1 second.
You're close. I just want to verify. Yeah.
One of your numbers is off. 225. 15 times 15. Think about it. 10 times 15 will give you 150. Then 5 more 15s gives you another 75. You get 225. So I could actually represent the length of the entire bottom here with radical 225. And to get this whole value as just a square root, I have to square my 4 So that becomes the square root of 16 still times that 3. Any questions with what I've done so far? I'm making everything radical just to make it easier to work with. Now, also, because this says to the nearest tenth, I could just evaluate what's the decimal form of that. That's another route that you can take. I just want you guys to work with radicals a little bit more because I know some of us are struggling. So this becomes radical 48, and I can determine what the difference between the entire length here and that red edge is by just finding the difference of these two radicals. So radical 225 minus radical 48, that would be one route that we can take. But since they asked to the 10th, we might as well show this the easy way. So if I hate tenths. I advise that you always go to hundredths because of money. Money is 2 decimal places. I always go to the hundredths. So 4 radical 3 comes out to be 6.928. So I'm going to go ahead and say 6.93. Keep forgetting, you can't erase like that. So if that red edge was 6.93, then 15 minus 6.93 will be my green edge, and that is 8.07. Or if you were going to the nearest tenth, like they asked you to get 8.1 there, you now know your bottom base, your top base, and your height. So from there, we can solve it. If I solve it by breaking it up into 2 triangles, so we're not just using a formula, or sorry, not 2 triangles, 2 shapes. To find the area of this triangle, it's always half of the base times the height. So we'll say area of the triangle is 1/2. I'm going to do 1/2 the height times the base because that's going to be easier. The base of that area was 6.93. Gives me 2 times 6.93. And that'll give me 12, 13 point something awkward. 13.86. And that'd be meters squared. Then the area of the rectangle, well, that's a little bit easier. That's just base times height, or whatever 2 dimensions you want to call it. 8.07 times the 4. .28, and although mine is more accurate than theirs, you should have gotten something extremely close to the total area being 46.14 meters squared. Does that match up with what you were looking for? Sorry, Hannah asked that. Is that? Yeah. The other method would be directly apply that trapezoid formula. Half the sum of the bases times the height. Other questions from 9-3.
It's a tough homework. I will not tell you that it's easy. It is a tough homework. You could utilize, you could utilize that here again. Set up a 45-45 special right triangle. Because I could drop a line or draw a line or whatever you want to call it right here. And then I could find out that this also has to be a 45. I know that this would also be 1.8, so this section right here would actually be 3, which means that that's 3. So you actually find out that the height of your trapezoid there, because the height is always the distance between your bases, that height would have to be 3. So without even computing any work for that, we can find out the height just by relating the 45-45 special right triangle.
Special right triangle has equal sides.
If it's a 45-45, it has equal legs. The hypotenuse will never be equal. Other questions? 9-3. Going once. Going twice. Moving on. 9-4. That's the one thing I don't like about getting to Schoology through our portal, is when the portal logs you out, Schoology logs you out. Not chapter 8. Polygons in the coordinate plane. Questions on 9.4. If I pull up the homework, determining what. So what's the difference between scalene, isosceles, and equilateral? And I will show you something here that might blow your mind.
So we have scalene, isosceles, and equilateral, right? How many sides do scalene have that are the same?
0.
None, right? How many sides do isosceles triangles have that are the same?
2.
And how many sides do equilateral have that are the same? Anyone know the trick I'm about to show you? Isosceles. The top and the bottom of the eye are the same. Equilateral. Yes, you know equi or equi means same. 3 lines that are the same in the E. In the S, there's none. It's just one curvy line. So isosceles, 2 that are identical. Equilateral, 3 that are identical. A student told me that. Thought it was sweet.
This sweet.
Yeah, said I will never forget that ever. Not that, you know, once you learn it pretty hard, like equilateral, okay. I just remember scaling just sounds weird, so it sounds like nothing is the same. But yeah, the isosceles versus equilateral, I thought that was cool. Good memory trick. What's up, John?
Nothing, was just that we had a general question about it, so that's the
Okay. We're on 9.4. We're almost done with chapter 9, so I'll be back in a second. Anything from 9.4?
I was kind of wondering, like, what are, like, all the classifications that you can kind of have for, like, the quadrilaterals? Like, 'cause
So there's a really good Venn diagram. I'm going to see if I can find this. That classifies quadrilaterals based on what characteristics they show. But so the main ones that we've worked with, obviously the base ones, square, rectangle, rhombus, trapezoid. Then we get into kites and different objects like that. So classifications of quadrilaterals. So here's the Venn diagram that I was talking about, because a square is a rectangle that is also a rhombus that is also a parallelogram. A rhombus is a parallelogram. A rectangle is a parallelogram, but a trapezoid is not, and neither is a kite. And there's no relationship between trapezoids and kites that make them overlap. But if you really want a good what makes it what it is, here's your good descriptors. And trapezium we haven't used yet because trapezoid has a pair of parallel sides. A trapezium does not. So it's kind of like a scalene quadrilateral if you want to think about it like that. But yeah, there's our main classifications. The one that they're missing there is kite. What makes a kite a kite? So if I draw, actually I'll just search it because it'll be better than mine. Yeah, 2 pairs of congruent sides that are adjacent to each other, and that's a really bad, that barely looks like a kite. Do you know it? Once I pull this up, you're going to know it. See it?
Oh.
The diagonals meet at a 90-degree angle, and these opposite angles are equal. So 2 pairs of sides, each pair is made adjacent, so like these 2 sides up top and these two sides at bottom, those are your pairs. Angles are equal where the pairs meet. The diagonals meet at a right angle. One diagonal bisects the other one. So it's your, if you look at the kite like this, your vertical diagonal bisects your horizontal diagonal. But it's always your long diagonal bisects the short diagonal. So that pretty much is everything that you need for classifying. So obviously 7 is the only one that looks like it might be a kite. So you got to go through and check. Are these equal? And you don't actually have to do the distance formula. You're going to say, do they have the same change in location? So do they have the same rise run? That would mean they're equal. And then does this bisect that? Other questions? 9-4. This, obviously, you'll need graph paper for it. So I have tons of graph paper. Feel free to take a pile home with you. No other questions. 9-4. Going once. Twice. Sold.